So as Michael just said, this is the Mars Orbiter for Resources, Ices, and Environments. We have a group of people that have worked this particular science and these science goals as part of the NEXAG mission report, as well as the ISAG report, and have been involved in a variety of other activities that have been looking at ice science and environmental transition science. And because we didn't have a lot of time and we didn't have a lot of money associated with the mission concepts. And so we wanted to keep it focused and facilitate discussion. The other thing that I want to note here is that although MORIE was merged with MOSAIC, and this was in order to leverage the orbiter studies, which are similar between the two missions, these So the motivation for this mission is that there are new discoveries in ice and climate. We have a number of discoveries of ice in new places. In particular, this provides a record of recent climate variations. We now have a ton of evidence for regional shows that there may have been a massive ice unit associated with scallop depressions in Utopia Planitia. In addition, we have scarps which expose buried ground ice, as shown here in the middle image in the upper top. There are impacts which expose ice down to 39 degrees north latitude, as shown. And ice has been found to be ubiquitous in the lobate debris aprons. In addition to the ice science, we have additional modern surface changes that we continue to observe and continue to catalog numerous additional instances, including recurring slope linea, gullies and changes in gullies, and dune migration. A much more complicated history, evidence for diverse aqueous environments. As shown in the image, which is from Bethany Ellman's paper, we have a wide range of alteration environments that span an uncertain age. We have transition from valley networks and potential outflow channels. We have potentially open water systems transition MSL. There's been a persistent in Gale Crater that lasted for probably 1 million years. We know that there have been transient wet and dry environments at Meridiani Planum. The paleoclimate models that we have don't predict persistent warm conditions, and so there's a major uncertainty in the timing, the duration, and the nature of these earliest aqueous processes. In addition, there's been tremendous interest in subsurface water ice as a resource. The Mars Subsurface Water Ice Mapping Project, SWIM, is led by my co-author Than Putzig, and this works to integrate the best available data from MGS, Odyssey, and MRO in order to find buried water ice that might be used as a resource that have used the thermal data from MCS and Themis, and these are extending the boundary of known buried ice closer to the equator. At the same time, the image on the right shows that there's a sensing gap. So what we can sense with the thermal data and Sherrod surface returns is something less than about 5 meters, something greater than about 20. So there's this transition zone between 5 and 20, which leaves a sensing gap where we really don't know if there's ice, and it's critical to know what the volume there is in order to understand ice as a climate signal. So a new orbiter can actually address these discovered formation conditions for surface and subsurface ice reservoirs. We can do more advanced thermal detection, mineral detection, and better stratigraphic reconstructions of the geologic, sedimentary, and geochemical record. And at the same time, we can do resource mapping that uses the same information as we need for our science. And there have been a number of past studies. The Orbiter Science Analysis Group in 2015, which emphasized the distribution and origin of ice reservoirs, environmental transitions, and the potential for both water and hydrated minerals to be resources. There have been a number of reports coming out of the National Academies of Science, Engineering, Biology, and Planetary Science for the next decadal report, the decadal midterm review report, and an astrobiology strategy. And then most recently, MEPAD commissioned an ice and climate science analysis group, which also recommended an orbiter in order to address this ice science. So conference calls, and the goal here was really to look at the science trades, in particular looking at INSAR versus PSAR and sounding, and also looking at LIDAR. We wanted to explore the imaging trade space of what do we need for spatial resolution, color, and coverage. We wanted to look at the shortwave and thermal infrared imaging spectrometer. And we wanted to, started with a number of previously published reports. We wanted to establish a set of MORIE-specific science questions and define the instruments and mission requirements. We had a TeamX architecture meeting in February, which was really a cost scoping exercise. We had a face-to-face meeting in February, and then we had our TeamX mission design early March and managed to get that in just before the whole COVID-19 managed to derail everybody's travel. And our final report will be due at the end of July. So we have a science theme which is focused on the evolution of a habitable world, and that leads to two primary deposits linked to current, recent, and ancient climate, and how does the crust record the evolution of surface environments and their transition through time. We then also have a resource theme, fueling future exploration, and we're interested there in ground ice serving as a resource, the potential for hydrated minerals, and how that affects access to potential resources. These key questions were traced to our primary science objectives. So I'm not going to spend a bunch of time going through the MORIE Science Traceability Matrix. Just to say that these key questions were linked to then 8 objectives for the physical parameters, as well as approach and measurement requirements. And so the details of this will be both in the posted presentation and then also in our final report. And I want to point out here that the resource objectives don't require any new technology or new instrumentation. We're using the same techniques as we're using to approach the science. Then we're linked to our instrument payload, and each instrument then is either primary, as denoted by a check mark, or it's supporting, as denoted by an S, for each of our science objectives. And then those same instruments will support the resource objectives. So we're looking at a synthetic aperture radar imager, as well as radar sounding band imager. We're doing thermal infrared spectroscopy. We have a wide angle color imager, and then black and white stereo context cameras. And I'll spend a little bit of time on each of those instruments. So for radar, we have 2, both radar sounding and radar. And why we have 2 is are going for vertical resolution, and the sounder will provide better vertical resolution with a goal of a ½ meter in ice, whereas the SAR actually provides an imaging mode at 100 meters per pixel and potentially higher resolution than that in a spotlight mode. And as shown in the images on the right, much more surface detail of the same location that you see over visible imagery, which is the inset. And then sounding from a terrestrial example shows that using P-band sounding in the Greenland ice sheet, you can actually resolve sub-meter layers in the ice. So why P-band? Which is shown as the here, in a study by Pettinelli et al. She looked at a variety of both dry soils, but also ice-cemented soils. But looking at dry soils with scatterers, the lower frequencies, 225 megahertz and 450 megahertz, will get us 10 to 25 meters into, so that really puts us in the sweet spot. There's currently a sensing gap. The higher frequencies at 900 megahertz and 1200 megahertz only get a few meters into the soil. That's noted by the blue lines here. And so the opinion of our team was that these higher frequencies are not going to get us much more than we're currently getting in terms of our shallow surface detection. In the polar layer deposits better than we can currently do with charade. And these lower frequencies and sounding will help us do that. These lower frequencies are also less sensitive to surface scatterers, and we're interested not just what's in the near surface meter, couple of meters, we're actually interested in the ice extent and the sound deeper layers. We're also interested in defining the lowest latitudes where ice is near the surface, and that likely is going to occur under a few meters of dry overburden. So we want to be sure that we're penetrating through the dry overburden in order to hit the ice that might be more deeply buried closer to the equator. Generation shortwave infrared imaging spectrometer from 1.3 to 4.2, spectral resolution less than 10 nanometers, 5 meters spatial resolution, as this region is best for alteration. The image on the right shows the spectral sensing history of instruments at Mars with the vertical axis. Is a step up from current CRISM targeted observations and covering these wavelength ranges, which are critical for alteration. At the same time, we have a Mars far infrared emission imager, Mars Fire. We're going to do a shared telescope between the 2 instruments that saves some mass. 20 channels class and circa 100 meters spatial resolution. So that puts us right on top of the Themis IR multi-channel imager, but MarsFire will extend the wavelength range out to 25 microns and will have much better spectral fidelity. And so this will do a better job at actually identifying those primary silicates and and so we're going after key questions. What's the nature of water and atmospheric chemistry driving the alteration? We want to be able to look at solid solution series, as well as do a good job of discriminating different types of alteration minerals that may have similar spectral signatures. And in order to understand if the transitions were resolution of sedimentary sequences, evaporative sequences. So in order to unravel that history, we need higher resolution and better spectral fidelity. For the cameras, we have a color imager, which is a 1 meter color imager from 0.4 to 1.7. This actually complements the spectral instruments. Image on the upper right is a Cassis image of an icy crater. We're actually going to do better than Cassis, and we're going to have more colors. So we are baselining 20 channels in this wavelength range at 10 to 60 nanometer band passes that can also discriminate water and CO2 ices. There is an opportunity with time delay integration to do solution. Is a MARCI image, daily global map from MARCI. And so we have a Maverick wide angle camera, which would also do daily global mapping, but again, with filters in the near infrared to discriminate water and CO2 ices so that we can actually pull apart the seasonal ices in the cap as a camera instrument. Is stereos at roughly 5 meters per pixel. These help with clutter mitigation in the terms of the radar simulations. We can also look for new ice exposing craters, and we can get better digital elevation models in the PLD. So we had a exercise, and instruments were using analogs from past missions that happen to be in the JPL database. JPL also has 2 cost models that they can run, prior Mars missions as well as prior New Frontiers missions, and we used power and mass as a proxy for cost. We started with the limit, as requested, we used FY $25 and 50% reserves, but we also reported 30% reserves as something that's more usual and cost numbers that people are more familiar with. We pretty rapidly converged on solar, electric, rather than chemical propulsion. There didn't seem to be a big cost difference between those two. From a orbit and a 90-degree orbit allows us to get direct nadir views and do sounding directly in what's currently the polar gap, that 3-degree gap directly over the poles. And the science team was really excited about this opportunity to do sensing nadir directly over both poles. And this will allow us then to also do some time of day coverage. So the table then here just shows the options that we explored in terms of that costing exercise. The numbers 1 through 12 are the numbers that we explored. I want to point out that in addition to our nominal payload, we looked at a high-rise equivalent image model, but this did allow us to do a strategy for our TMX mission design, including potential D-scopes that would then potentially fit into the New Frontiers cost cap. So the first row here, option 7, is our full up MORIE mission. And the first thing we wanted to have a look at, potential D-scopes. We were baseline, if we have to mode, then that's one potential D-scope would be dropping one potential instrument. The next potential D-scope is actually dropping one of the spectrometers as well as the high resolution imager and the stereo, and we would do stereo through repeat acquisitions of sites. And then a final potential D-scope that SAR do the sounding mode again. So we went into Team X then wanting to do the full up mission design as the first set of design points. We had a combined telescope for the NG Swiss and MarsFire spectrometers. We didn't get a chance to talk to the JPL. Design point was a combination at a single central frequency of 400 megahertz. We then were able to look at a D-scope primarily to look at the cost impacts, which would still meet our science objectives and address both ice and environment science themes. That's dropping one of the spectrometers, dropping the high resolution imager, and one of the first 2 days look at the first full-up mission, and then we had a chance to finally look at what we consider to be a science floor, which would only address the ice and resource themes, which would do dual band sounding and SAR, so we could get sounding in 2 center frequencies and SAR in 1, and retain the stereo cameras. And all of these Falcon 9 with healthy margin. So I don't want to spend too much time on the design summary, but the instruments included the full payload with the combined SAR sounder. We did actually get detailed reports from TMX on command data systems, on ground systems, on telecom, attitude control, structures, radar, panels out to the sides, and then the high gain antenna at the top. And I'll talk in another slide about where the instruments go and are looking. So we baselined a 2-year Mars mission, 2 Mars year mission. With solar electric propulsion, it takes about 2 years to get there. So the first orbit and spend a full Mars year in that 90-degree Mars orbit, and then transition back to sun synchronous at the end. And so that's so we can see a full Mars year, both polar caps in both observing orientations. The graphic on the right shows a typical data sizing orbit. Typical day in the life, where we do imaging optical instruments on the day side. We have radar working on the night side, as well as doing comm and building in eclipse times as well. So here's the spacecraft deployed, the shortwave infrared spectrometer, as well as the Mars Fire. The Maverick wide-angle camera is this little blip, and then the 1 meter color imager in center of the nadir deck, and then we have the 2 stereo dual cameras. The spectrometers in the color imager are designed to only collect targeted observations depending on the Earth distance. We'll also observe targets on the night side so that we can do thermal inertia in order to constrain those near surface potential ice resources. The polar SAR sounder operates at night, alternating between sounding and SAR modes. And then Maverick wide angle camera collects continuously on the day side. And we will have acquired about 50,000 targeted sites. So the takeaways from MORIE: this mission can answer fundamental questions and respond to major new discoveries in ice, environmental transitions, and climate. To best address the global distribution of ice reservoirs and the current sensing gap, design is straightforward and does not present any novel technical risks. CEP has not been used for Mars, but should present no major technical challenges. The cost savings that we saw was primarily due to the reduction in the number of instruments. The spacecraft bus was really a second order effect. And costs, in particular, the costs for the radar are $25 but it could be within scope if there were contributions of instruments or hardware and further design maturity. And that's all I had, and I'm happy to take questions. I'm not hearing anybody.
Oh, thank you. Finally.
There you go, Michael.
Thank you very much, Wendy. I was questions from Suniti. What are the team's plans for integrating regional bulk geochemistry observations from prior missions with seismic and thermal probe observations for insight into the moon's, oh, I got the wrong one here. I was thinking, wow, that's an unusual question.
I can talk about integrating with prior mission geochemistry. Certainly that's
right. I was going, does this person listen to the right talk? Okay. With their audio while you're talking.
Oh, okay. So let me go back to the camera slide. So the color imager is a 1 meter imager. So that's better than Cassis, which is for that color imager between 0.4 and 1.7, and those channels. We did some design work to select mafic mineralogy, iron oxides, as well as both water and CO2 ice features that we could resolve with narrow channels. So they're depending on the would return reasonable signal to noise for a 1 meter imager. We also potentially have a super resolution mode for this 1 meter imager, which could approach high rise resolution. So probably 30 to 50 centimeters per pixel in that time delay and integration mode. Deep field view the spatial footprint here, but circa 1 kilometer per pixel for the wide angle camera. And then the mid stereo cameras are roughly 5 meters per pixel, so CTX scale in black and white in order to do better stereo.
Sorry, provisions are being made for surface mission data relay.
So
perhaps a painful subject, but important.
Yeah, so I think that we baseline some typical COM, but that was not a strong focus of our discussion. But I think that certainly this orbiter could do that, and certainly it's on the. I think it's in terms of the band channels that we chose for the communications are consistent with being able to do communication with landed assets.
I don't see any more questions, Wendy.
That's fine. I can stop sharing. And
do you want to add anything before we move on to Rob? Or
I don't think so. The one I did relationship to ICE Mapper. So they started this before we heard about ICE Mapper in the president's budget. And that what we heard from ICE Mapper is that they're targeting these higher frequencies in order to go for the really near surface resources. And I guess I would just say that from our perspective, in order to really do the ICE science that we're sensing ICE, I think that our team would promote lower frequencies for that better penetration and getting into the gap that we currently have.